Hello, welcome to our series of videos on linear algebra. Today we look at the geometry of linear systems. And the question is, we have to consider the following system of linear equations in two unknowns with a unique solution. So here we've already been told that it has a unique solution, but what we want to look at is what happens when we plot these two equations. Let's call this equation 1 and call this one equation 2. So if we wanted to plot them on a graph, let's say we draw the xy plane. So it's our x-axis, our y-axis. If we wanted to plot x minus y equals 0, x minus y equals 0 is the same as x equals y. If x minus y equals 0, then x equals y. And we may already know that this is the line y equals x. But if we don't know that, we can plot some points, 2 points on the line, and then join them with a line. So for instance, if we pick x equals 0, then because x equals y, y must also be equal to 0. So we know that the point 0, 0 is on the line. And then we pick the value x equals 1. When x equals 1, let's say x equals 1 is here, then y must also be equal to 1. So we say that this point 1, 1 is also on the line. So if we get those 2 points and we join them with a straight line, we're going to get a graph of x equals y, or x minus y equals 0. Now we can plot this line also, x plus y equals 1, with the same method. Here we can say, okay, what happens when x equals 0? When x equals 0, we have y equals 1. So the point 0, 1 is this one that's on the line. Let me label it 0, 1. And then when y equals 0, x is also equal to 1. So that means that the point 1, 0 is on the line. Let me label it 1, 0. So we can join these 2 points with a straight line, and then we get a graph of that. So let's do that. All right. So here we've plotted the 2 lines and they intersect. The point of intersection is the point where we have our solution, or is a solution to the system of equations. And that is the point we want to note here, that when you have a system of equations in which the two equations or the 2 lines are not parallel, then they are going to intersect. And the point of intersection is going to be the solution of the equation. So here, let's try to guess what the solution is. From the graph, if we come all the way here and also come all the way here, what do we have? This is probably the point half, a half here and a half there. That means that x equals half, y equals half is probably a solution. Now this is an approximate solution because we don't have an exact graph, but we can determine the solution by solving these two simultaneously. One way we can do that is by using elimination. If we add these 2 equations, what do we get? We get 2x. The minus y and the plus y cancel, so we get 2x equals 1. That means that x equals half, which is what we got from reading the graph. And then we can substitute this value, x equals half, back into one of the equations. For instance, if we use equation 1, x minus y equals 0, we already saw that x minus y equals 0 means that x equals y. So if x is half, then y is also half. So that is the solution to the system of equations. Now let's look at another system. Here we consider the following system of linear equations in 2 unknowns with no solutions. If we observe carefully what's going on, here we have x plus y equals 1. And then we have here also that x plus y equal 2. So you have two numbers, x and y, their sum is equal to 1, and at the same time, their sum equals 2. So immediately, that should ring a bell that there's probably something not going on well. You cannot have those two being true at the same time. That leads to a contradiction. So that is how you can end up with a scenario where you have a system of equations with no solutions. Now, if we try to graph, we already graphed x plus y equals 1. We saw that it was the line that goes through here. So this point is 1, and that point is also 1. So both the x and y intercepts are 1. And then we also have x plus y equals 2. So this is precisely the line with x-intercepts 2 and y-intercepts 2. So we can draw that. And we see that these two lines are parallel and they're not going to meet anywhere. So that is how we end up with a situation where we don't have a solution to our system. Let's look at another example. So here we are being asked, when do we have infinitely many solutions? So this is giving us an example where we have infinitely many solutions for us. We have x plus y equals 1, and then 2x plus 2y equals 2. If you notice that 2x plus 2y equals 2 is what we get when we multiply this equation by 2, then that's very good. So equation 1 times 2 gives us 2x plus 2y equals 2. That means we essentially have the same equation. If you have an equation and you do the same thing to both sides, you don't change it. So here we multiply the left-hand side by 2 and we multiply the right-hand side by 2. So we essentially have the same equation. And if we graph them, we're going to see that their graphs are the same. Their graphs overlap. So x plus y equals 1 again. That's this one. And if we want to plot 2x plus 2y equals 2, we can proceed this way. We can say, okay, first let me label this. We have, this is 1. This is also 1. If we say, what is the x-intercept of this and what is the y-intercept of this, that's going to help us plot. So what happens when x equals 0? When x equals 0, we have 2 times 0 plus 2y equals 2. Now 2 times 0 becomes 0, so 2y equals 2, then y equals 1. And then when y equals 0, what do we have? We have 2x plus 2, 0 equals 2. That means 2x equals 2 and x equals 1. So both the x and y intercepts of 2x plus 2y equals 2 are also 1. That means that the graph of that is the same thing as this one. So every point on this line is a solution. That's what it means. Or put another way, whenever we have x and y such that x plus y equals 1, we have a solution. So 0, 1 is a solution because 0 plus 1 is equal to 1. Any two numbers that add to 1 are a solution. So we can have 1/3, let's see, 1/3, 2/3. That's a solution. We can even have negative numbers. We can have -1 and 2. And if you look at the graph here, -1 could be somewhere here. And you see that the corresponding y value is 2. So -1, 2 is a solution. Any two numbers which you can add to get 1 will be a solution. So 100 minus 99 is a solution. So we have infinitely many solutions. We simply cannot count how many solutions there are. So This idea in two dimensions, or this idea when we have two unknowns, we have a situation where we have infinitely many solutions. We have a situation, this one, where we have no solutions. And then we have another situation where we have exactly one solution. These ideas can be extended to when we have more than two equations, when we have three or four or five, as many equations as we want. So in particular, we want to look at the situation where we have three equations or three unknowns, three equations and three unknowns, or we have three unknowns. When we have three unknowns, the the equations are going to represent planes. And so the question becomes, when are your planes going to intersect? And when are your planes not going to intersect? When you have this situation, you have three parallel planes: plane 1, plane 2, plane 3. They are just parallel to each other. They simply do not meet. And it's analogous to the situation we had here, where you had two parallel lines, and because they were not going to meet anywhere, there was no solution to the system. You could have another situation where there's no solution because two of the two of the planes are parallel to each other, and then the third one is crossing them. So that'll be this scenario. And then you could also, the case where you have a unique solution is this one, a unique solution, because you have all the three planes intersecting, and they intersect at exactly one point. This is the point of intersection. So you have your first plane, your second plane, and your third plane, and then they intersect at a point. And then you have this scenario where there's no solution also, because the planes are just cutting each other, and you do not have the three of them coinciding. So the first one intersects the second one in a line, but then the third one also intersects the first two, in two places. So no solution. And then you have this scenario where you have the three planes intersecting in a line, this line. So all the three planes go through this line. So you have agreement there. But what's going to happen is that in that case, you're going to have infinitely many solutions, because any point on that line, any point on that line is a solution. So that is how we extend the ideas in two dimensions, or in systems where we have two unknowns, to systems where we have three unknowns. And the same idea extends to when you have even more unknowns. Now we have this problem where we are trying to find out how many solutions the system has. And we can do that by elimination, where we are trying to simplify the system to find a solution. So by elimination, we can find if the system has a unique solution. We can also find if it has infinitely many solutions, or if it has no solutions at all. So let's see. Let's try to first eliminate x. We eliminate x. Let me first label the equations. Equation 1, equation 2, equation 3. So if we subtract equation 1 from equations 2 and 3, what do we get? So first subtract, let me see, equation 2 minus equation 1. What does that give us? That gives us minus 3z equals minus 3. And then we subtract equation 1 from equation 3. What do we get? We get minus z equals -1. All right. So that elimination process was quite simple. By subtracting equation 1 from equations 2 and 3, we end up with a new equation, minus 3z equals minus 3, and then another equation, minus z equals minus 1. So let's call this equation 4 and equation 5. Now these two equations came from equations 2 and 3. We'll bear that in mind. So having eliminated x, we've also eliminated y, and then we will now want to eliminate z. We can do that by multiplying. We can also do that by adding directly after multiplying. As in, we could multiply equation 4 by minus 1 so that we have 3, and then we'll divide that by 3 and then try to add. But we could also just use equation 5 instead. So we say, well, if you have equation 5 times 3 and you subtract it from equation 4, what are you going to get? So equation 5 times 3, well, that gives us minus 3z equals minus 3. Then we can subtract that from equation 4. So this equation 5 times 3, let me just write it, minus 3z equals minus 3. Now we want to, let's call that equation 6. Now we want to subtract. We can say equation 5 minus equation 6. What does that give us? Equation 4 minus equation 6. Let's get that right. Equation 4 minus equation 6. When we do that, we have minus 3z minus minus 3z. So that gives us 0. Then we have minus 3 minus minus 3, also 0. So by subtracting equation 6 from equation 4, we end up with 0 equals 0. So we have equation 1. We used it to eliminate x and y from equations 2 and 3. That gave us equations 4 and 5. And then we multiplied equation 5 by 3. And then we subtracted it from equation 4. And that has ended us with 0 equals 0. So let's see what we can do with that. Equation 1 is maintained, so we have x plus y plus 2z equals 5. Equation 2, the representative of equation 2 that we have now is essentially the 0 equals 0. So let me write that. And then equation 3 is what we ended up with. We can take it as equation 6 or equation 5. So let's say we use equation 5 where we have minus z equals minus 1. That's the same as z equals 1. So z equals 1. Now, what does this mean? This means that, yes, z equals 1, but where we're supposed to get y, we now have 0 equals 0. So that means that we can pick any value for y. And then x plus y plus 2z equals 5 is the restriction or the relationship between x, y, and z. So if you pick x equals 1, if you pick z, if you have z equals 1 and you pick y also equal to 1, what's going to be your value for x? That's the way to think about this. So you can have that, and then you say, well, what about if I pick y equals 2? Then I know z equals 1, so what's going to be my value for x? And then I pick y equals 3. So I can pick any value for y. So eventually, to generalize, I say let me pick y equals t, where t is a parameter. So t is a parameter that we can set to anything, to 0 to 1, -1, -5, any value we want. And that is going to determine the other variables. So when y equals t, um, z, as for z, it's equal to 1. We already found it. But what about x? We have x plus y plus 2z equals 5. So let's substitute the values of y and z here. So we have x plus y is now t, and z is 1. So plus 2 equals 5. That means that x equals 5 minus 2 minus t, which is equal to 3 minus t. So picking x, sorry, picking y equals t, we have that because z equals 1, x must be equal to 3 minus t. And t can be absolutely any value. That means that our system has infinitely many solutions. And if we go back to our diagrams, this is the scenario which we have. The systems, the planes that represent the equations are all intersecting in a line. And so we have as many solutions as there are points on the line, and there are infinitely many points on the line. So we have infinitely many solutions. Now we can also have a situation where we don't have any solutions. That is, we can create that kind of scenario. For instance, when we use elimination to get to 0 equals 0, if we had somehow got into a situation where we had, let's say, 0 equals 1, then there's no way to resolve this, because 0 can never be equal to 1. 0 is simply not equal to 1. So if you perform the steps in elimination and you end up with something like that, then we say your system is inconsistent and there are no solutions. And we're going to see examples of this in the future. Later. See you later.